Okay, so let me return to the second question that I had about singularity characterization. Ignore the typo here where I say formation. My claim was that if you take a torus that is rotationally symmetric with respect to some axis in Euclidean space, then the total curvature is actually bounded near its singularity. And one thing that I should clarify, because I didn't actually mention it in the statement of the theorem that I showed you, is that everything I'm talking about just for this part, not for the last part, but just for this part is in R3. The methods that I use to show this are very specific to R3. I just want to get that out of the way. But anyway, you have some torus that's rotationally symmetric about this axis. So you can think about its cross sections, or one of its cross sections as just being a curve like this. And what you'd like to know is whether or not, as the torus expands towards the central axis, whether or not it winds up reaching it by the extinction time. If that happened, you would have like infinite curvature here. But if it didn't happen, you would have finite total curvature by the singular time. So we want to rule this possibility out. And you can verify just by kind of, like properties of the generating curve that the NT is going to stay embedded, despite the fact that this might not always be true for inverse mean curvature flow. For this sort of initial data, it will be true that NT is going to stay embedded. So you know that a singularity does happen by the previous result. But now I want to characterize it. So let's talk about that. So the main tool that you normally use for singularity analysis under mean curvature flow is parabolic rescaling. Normally you take a solution to mean curvature flow, you rescale it in space and time so that you kind of magnify the singularity as you also make the time interval for the solution bigger, and then you hope to obtain some tangent flow that you can then analyze. Now, this entire procedure won't really make any sense for inverse mean curvature flow. And the reason is just because an equation like this, an equation like this won't respect the standard parabolic scaling. So you can't analyze inverse mean curvature flow with tangent flows, essentially. But you can still just rescale at each time step the space variable, basically. So we're going to show by contradiction that you can't have pinching down along this axis of rotation for a torus by contradiction. So let's say that the distance between each flow surfaces and the axis of rotation is y of t. And let's assume for the sake of contradiction that the limit as you approach the singular time of y of t is 0, so that you have this pinching. You can then rescale each flow surface by 1 over y to the t. So in other words, you take nt and you scale it so that it stays a distance 1 away from this axis, which if y of t is going to 0, we'll just keep making it bigger and bigger. And what we're going to show is that the limit surface that should exist for this nt actually couldn't exist by an energy estimate. So first of all, let me just say that maximum principles are always great ideas to use if you want to study geometric flows. And the maximum principle for inverse mean curvature flow tells you that the initial mean curvature always bounds the mean curvature above throughout the lifetime of the solution. So the max over nt of the mean curvature is less than or equal to the max over n naught of the mean curvature. And that means that mean curvature, at least, is uniformly bounded. So if anything is blowing up with the total curvature, it needs to be the trace-free part of the second fundamental form, which is blowing up, not h, which is very different from mean curvature flow. Now, the reason that this is useful is because what if the distance to the axis of rotation were going to 0 near a singular time. That would mean that if you blew each flow surface up by 1 over y to the t, these scale factors would be going to infinity, and that would tell you that the maximum value of the mean curvature over the rescaled surfaces would need to be going to 0, right? Mean curvature would scale by y of t, so if this is bounded above, then this needs to be going to 0, provided that y of t approaches 0. And that's everywhere along the surface. So if you want to look at this as like a problem of blow-up limits, right? You want to rescale near the singular time to obtain some sort of blow-up limit. Any blow-up limit that you could possibly obtain for inverse mean curvature flow, and again, just in the space variable, we're rescaling, not the time variable, but any possible blow-up limit you could obtain for inverse mean curvature flow should be a minimal surface, right? Because mean curvature is going to 0 everywhere. Now, in the case of a rotationally symmetric embedded torus, this is very useful because we should expect, and I'll justify this further in a minute, but we should expect that if it converges to anything, it should be a complete minimal surface of revolution in R3. Well, we know what it could possibly be at that point. The only candidate limit surface, if you're in R3, for this sort of data, should be a catenoid. And a catenoid has as its generating curve a catenary curve, just as a reminder, like this. Okay, so that's the goal. We would like to show that the rescaled flow surfaces could not converge to a catenoid. So once we rule out blow-up catenoids as blow-up limits of n tilde of t, we would obtain the desired bound on the norm of A, because we would know that y of t were bounded away from 0. And the key ingredient to accomplishing this is the Gauss-Bonnet theorem. So remember that the Gauss-Bonnet theorem tells you that if you have any surface with boundary in R3, which I'll call sigma, the integral of its Gauss curvature is equal to 2 pi times its Euler characteristic plus the boundary integral of its geodesic curvature. And something that I'd like to point out before we move on is that Gauss-Bonnet is scale invariant. So if you take a given surface, lambda, and you scale it up by anything, you get the same value for k d mu. So what we're going to do is we're going to pick these nice uniform subsets of NT, which after rescaling should converge to a catenoid. And then using Gauss-Bonnet, we're going to show that they can't converge to a catenoid because the integral of their Gauss curvatures is not going to be big enough. So the exact way that you do this selection of subsets is you take two parallel planes, both perpendicular to the axis of rotation, and you consider the part of NT that lies between these two parallel planes and also lies closest to the axis. So I just drew a cross section here. This right here is the axis of rotation. This is the generating curve, so just a cross section of n of t. And the region S of t that we're interested in is the region in between these two fixed planes, P1 and T2, which is also closest to this axis. You can show that this region S of t, if you pick P1 and P2 the right way, should be graphical. Now, using elementary properties of the flow, which you can check the paper if you want any more information on, plus Gauss-Bonnet, you can show that the integral of the Gauss curvature just over S of t stays a little bit smaller than 4 pi. So you need to also know something about the geodesic curvature here and here in order to make this conclusion. And that's where actually the one-sided avoidance principle for inverse mean curvature flow comes in. But the point is you can make the integral over S of t of this quantity a little bit smaller than 4 pi. And then you know that if you blow these graphs up, they should converge to a catenary graph, which you can show rigorously. Now, you can just, if you look at the generating curve for a catenoid right here, conclude that the integral of Gauss curvature over any catenoid should be exactly 4 pi. So once you've established that the blown up surfaces converge in C2 to the catenoid, you'd have your contradiction, right? On the one hand, the blown up surfaces S tilde of T should have Gauss curvature less than bounded away from 4 pi by the scale invariance for Gauss-Bonnet. And on the other hand, their limit would have Gauss curvature, integral Gauss curvature exactly equal to 4 pi. Maybe just to make this all clear to myself again, you take S of T, you blow it up by a sequence of scale factors to go to infinity. You should expect that S of T converges in C2 topology to some catenoid by the maximum principle. And the reason that it can't converge in C2 to some catenoid is because the integral of K over the catenoid is 4 pi, and the integral of K over S tilde of T needs to be bounded away from 4 pi. So it's actually rather simple. I know that this is not the most constructive proof method, but something to be said that you can show this with just elementary flow properties in Gauss-Bonnet, more or less. And once you know that y of t cannot approach 0, via a bound on h, you can get a uniform estimate on the total curvature up to the singular time. And before I end this talk, I'd like to say, we now know that for this family of surfaces, you obtain some sort of a limit surface thanks to a bound on the total curvature. And the natural next question, which people who study singularities of mean curvature flow might also be interested in answering, is this a general behavior for singular solutions? Do singularities always have bounded total curvature and therefore have some sort of limit surface at the singular time without rescaling? And I can't provide the full answer to that yet, but I think it's also noting that if you apply Gauss-Bonnet to any embedded flow solution in R3, you can at least get an L2 energy estimate on the total curvature, which only depends on initial data. So the fact that you can get an L2 estimate on the total curvature up to any possible singular time, at least in R3, hints that maybe you can get an L infinity estimate up to the singular time. So it's possible that the behavior that is observed for this rotationally symmetric torus is a more general feature of solutions to inverse mean curvature flow, which would be pretty interesting from the viewpoint of heat equations, since normally you don't have flow surfaces without rescaling. At any rate, this is at least the borderline case of the Sobolev inequality for n equals 2, this L2 estimate. So you're close to at least having some sort of limit surface, if this is true. And that might be a further direction to go. So I'm glad you stayed on for this whole thing. This talk has gone extinct. So thank you very much.